Hey everyone, my name is David Hull, and today I will be presenting my findings from our Physics 2211 lab on projectile motion. So let's start with a quick introduction. The purpose of this experiment was to observe, analyze, and compare the projectile motion of an object using computational models, and during this we considered the effects of drag force and gravity. For a quick preview of my experiment and results, my group rolled a lacrosse ball off a table to simulate projectile motion and found that the computational model using drag force was much more accurate to the actual results than the model that only considered gravity. Before we get into the data, there are a few important equations we need to discuss. First is Newton's second law, which we discussed in the previous lab. It states that the force is equal to mass times acceleration. And then we apply the momentum principle to this equation, and we can derive the velocity update formula shown on the bottom left of the page. Also, we will use the position update formula, and this will be used iteratively because the velocity in this experiment is non-constant. This non-constant velocity is due to the force of gravity, denoted by Fg equals mass times g, or 9.8 meters per second squared. And then lastly, we will use the drag formula, which states that the drag force is equal to the proportionality constant times the speed squared times the unit vector velocity. Next, I'll discuss the procedure. The materials used in our experiment were a lacrosse ball and lacrosse ball, meter stick, and camera. The system was the lacrosse ball, and the surroundings were the Earth, so basically everything else. We recorded a video of the ball on the tracker and graphed that data in Excel. Then used GlowScript to find computational models for our experiment, one with drag and one without. After all models were created, I compared the data and made conclusions. Here's a video of our awesome experiment.
Alright, it's recording.
No, this frictional force is the same as this force.
Super fun.
Alright,
So analyzing the tracker data. I flipped the video and put the x-axis on the floor so that the data was all positive. This made it much easier to compute the graphs in later steps. You can see the projectile motion graphed here on the right, and we will be able to compare this to our other computational models, but the observed data is there in the green. Now discussing our computational models in GlowScript. I calculated the net force using the equations for drag force and gravitational force seen on that left side of the page. And then down on the left, you can see the position and velocity update formulas, which we went over earlier. On the right, you can see the initial conditions. The velocity vector was found using the change in distance over time of the first 2 points, and the initial position was given in tracker. 2 models were made with this code, the only difference being the value of b. For the graph that didn't include drag, the value of b was 0, and for the graph including drag, the value of b was 0.064. This value was found using a plug-and-chug method, comparing the observed data to the computational graphs. Also on the bottom left, you can see the code for the vector arrows, which we'll see on the next slide. Here you can see the visual representation of drag, velocity, and gravity on the ball. Gravity is directed downward, velocity is directed in the direction of motion, and drag is anti-parallel to that. Note that the model without drag would only have the 2 downward arrows and wouldn't have that orange arrow at the top. On the right, you can see the graphs of the observed data in green, the predicted without drag in orange, and the predicted with drag in light blue. So now we're going to compare the data and make some conclusions. As you can see, the graph without drag overshoots the observed data by a good bit. However, when we include drag in the predicted model, it is much closer to the real data. My data obviously still has some variation in error, however, it is pretty close to the real data. And personally, I think this was due to starting our projectile motion at its peak by rolling the ball off the table instead of throwing something up. Errors for the graph without drag would be neglecting air resistance, pretty obviously, as well as human error during the position tracking and error. We're not always going to get the center of mass correctly. Errors for the graph with drag would be caused by the position tracking as well, and then also incorrectly finding that experimental value of b that we discussed earlier that is used when calculating the drag force. What does it mean? Terminal velocity is when the net force is equal to 0, and in the case of this lab, we cannot find the terminal velocity due to the length of our experiment. However, we could find the terminal velocity in the computational model if we extended that time of the while loop, where mine was 0.433 seconds, because that's how long my video was. If we had extended that time out, we would have been able to find the terminal velocity. Lastly, if the ball was initially thrown straight up with the same initial velocity, it would take a longer time to reach the ground, since the full initial speed would be in the y component of the vector. This was found using the 2 formulas at the bottom of the page, t up and t projected. Thank you all so much for listening, and I hope you enjoyed.